Hello everyone, welcome to the channel, and today we are going to see interference of film, that is the interference of the reflected light. There is also a part of the refracted light which will be covered in the next video. You can also check it out from the link given in the description. So this is the exact uh, diagram of this whole incident. Let me explain the diagram first and then we can move on to the theory part. It's not that difficult of a proof. If you see here, it's the ray is coming from here. It's first getting reflected, a part is getting reflected, some part is getting also refracted. This refracted part is also again getting reflected as well as refracted. So the reflected part here, it travels back up and it goes like this. So if you see the whole diagram, you will see there are majorly 5 to 6 points. First, it is the point A, first where it was incident. Second is this point O, where the second part, the refracted part, was being incident. Third is the point C. Now, if you see E, D, and B, these are points which are made by us. These did not happen actually. So what we do is we first drop a perpendicular to the OC line. This O and C line, we drop a perpendicular, that is ED. So this is perpendicular, and we also draw a perpendicular to the line AB. Like we drop this perpendicular CB, which is perpendicular to AB. Okay. Now if you see, how do you see that this is I and this is R? We know that this is the angle of incidence and this is the angle of refraction, and by symmetry we can also say that these dotted lines and this dotted lines, these two lines are normal to the surface, and by symmetry we can say this is angle R and this is also angle R. This is the angle of refraction. Now how do you see that this is I and this is R? We see this because if you see that this is a this we know by Fermat's principle that this angle I equals to this angle R, right? So if this is angle I as well, these two angles are equal. This is angle I, this is 90 degree, so this is also again I, this is angle 90 minus I, right? If this is angle 90 minus I, this is also perpendicular, so this is by triangle law, this is I. Now if you see, how do we say that this is R? So if you see this, we have the angle R here, right here, right? Now this angle is 90 minus R. This is perpendicular, and that's why this is R again. You need to understand the picture well, then you don't have any confusion in the theory part of this whole procedure. Now what we do is we extrapolate this CO line, we extrapolate this until the A, the normal through A meets at a point E. If we see these two dotted lines are parallel, right? So this angle R is equal to this angle R. How do we see this? Because of alternate angles. If you see two perpendiculars and this is one line, this angle should be this angle, right? Now we come to the actual theory part. This is the thickness, the T, and this is mu because this is the refractive index of this medium. We consider this to be air, so we consider this to be mu equals 1. Now, if we come to the optical path difference, you see that this ray passing through A and getting reflected through A, this ray reaches a point B, and at the same time this transmitted ray or the refracted ray passes through A to O, then O to C. These two are perpendicular, so this thing and this thing, the ray traveled here in the same time as EO to OC. So we can say that the path difference between these two rays is del x equals AO plus OC into mu, because it is traveling in the refractive index, minus AB. Okay. Now we also know that mu equals sine I by sine R, right? If mu equals sine I by sine R, we can see here that sine I equals AB by AC by sine R in this triangle ADC. This triangle we have CD by AC. From here we can see that mu equals, this is the first point, this is the second point. From here we can see that mu equals AB by CD. That is AB equals mu into CD. Now if it's mu into CD, we can also put this AB out here in this equation AB, right? Now I need some space. I'll just write it down here first. So del x becomes, what is we see, mu taking common, AO plus OC minus CD, because we substitute mu CD here and we take mu in common. Now I need to create the space right now. If we keep all the other things in place, let this equation be, this is our main equation, we see that this angle R is equal to this angle R, right? By isosceles triangle law, we can say that AO is also equals OE. So we can put here del x equals, in place of AO we write OE plus OC minus CD into mu. We also write here OE plus OC is equal to EC minus CD into mu, or we can also write this as OD into mu, right? Because EC was the ultimate thing and we reduce CD from it. So OD into mu is the del x part. Now we see that in this triangle ADC, this ADC thing, or not actually ADC, we see in this triangle AED, this AED triangle, we see that cos of this angle, cos of R, this is perpendicular out here, right? At point D it is perpendicular, this triangle. So cos of R, use a different color, cos of R out here is equal to the adjacent side by the hypotenuse. So this is not OD, this is ED, sorry. So ED by AE. Now if you see by the isosceles triangle rule, this is the perpendicular, right, to the base. Now this thing, let's name this one P, AP is T. So by symmetry we can say that PE equals AP, so AE equals 2T, right? Now if we see that ED equals AE cos R, we can also write ED as 2T cos R, right? Because we substitute AE as 2T. Now we also know that del x equals ED into mu. Now ED can be written as del x by mu. So del x, we shift mu to the other side, 2T mu cos R. This is your main thing. Del x equals 2T mu cos R. I need to rub this. I'll just write this down. Del x equals 2T mu cos R. Now for bright fringe, we know that the path difference should be equals del x equals n lambda for bright fringe. BF is bright fringe out here. Now del x equals n lambda. Now see this reflected ray out here. These both are reflected rays, right? We know that when a ray is reflected, its phase angle changes by pi. What does this mean? We also know that del phi equals 2 pi by lambda del x, right? If you put pi over here del phi, you will see that the del x comes to be lambda by 2. So the path difference changes by lambda by 2 when it is reflected. So we can say for bright fringe, the corrected version becomes lambda by 2. In case of transmitted rays, you will see that this lambda by 2 does not come. And that's the reason the, what do you say, the formulas become just the reverse here. Okay, so del x equals n, we can substitute out here 2t mu cos r equals n plus half into lambda. This is for the bright fringe. Similarly, you can say that in case of dark fringe, we know that del x equals n plus half into lambda, right? If you plus half lambda here, you will see that del x equals n plus 1 lambda. We can also write this as some other constant, right? N lambda, let's say. If we have this n lambda, we'll put 2t mu cos r, 2t mu cos r equals this. Here, my friends, you will have the two equations needed from interference of thin film reflected light. Thank you. I hope you enjoyed the video. If you did, please hit the subscribe button and also share this with your friends.